In this video, we're going to learn how to represent hydrocarbons. So we can represent hydrocarbons by their empirical formula, their molecular formula, and their various structural formulas. So if you remember from grade 11 chemistry, the empirical formula is the lowest ratio of atoms in a molecule. The molecular formula is the exact number of atoms in the molecule. But the structural formula tells you the number of the atoms and their positions. So the structural formula is the most informative of the three types of formula because it tells us where the carbons and the hydrogens and the other parties will be bonded to one another. So the full structural formula shows us the atom, each atom in the molecule, and the bonds between each atom. So if we were to draw the molecule butane, it would look like this. So there would be the carbon backbone showing the 4 carbons in a line, and then all the hydrogens bonded off the carbons, like so. I forgot a bond there. So that would be the full structural formula. So the condensed molecular formula, it leaves out the bonds between atoms. And the way that one is going to look, if we draw butane again, we would draw it like so. So we would write CH3 for the first carbon, and then CH2, remember in the middle of the molecule, you don't have, you only have 2 hydrogens able to bond, and then CH2, and then CH3. That's one way of drawing it, or you could write it even more condensed if you wished. So CH3, the end carbons always have 3 hydrogens, and then brackets CH2, and there's 2 of those. So subscript 2 and then CH3. That's if you're really, really lazy. If you're drawing decane, for instance, with 10, I would see why you might want to use the one on the right, because then you could just say CH3 and then CH2 bracket with an 8 subscript and then CH3 at the other end. So the skeletal formula is even lazier than the condensed molecular formula. So this time only the backbone is included, and we don't even write the carbons, we just draw a series of lines. So the carbon atoms are found at the intersection of each joint in the backbone. So if we were to draw butane, it would be this. So this would be a carbon right here. This is a carbon, 2, 3, 4. That's butane in skeletal formula. Now, if you wanted to convert that into 2-butene, you would draw a double bond there. So that's 2-butene. That on from carbon 2 to 3, there's an additional bond. So structural isomers are molecules that contain the same molecular formula, but have a different arrangement of their atoms. And the more carbons you would have in a chain, the more isomers or rearrangements that can be made. So we'll draw 2 examples here. The first one is pentane. So we'll draw our 5 carbon chain like so. Fill in all the hydrogens. Now, pentane has the same molecular formula as this one. So I'm going to draw a 4-carbon chain with a methyl group up here. Fill in all the hydrogens, like so. So now let's just take a look here. So this is pentane. So there's 5 carbons and 12 hydrogens. Over here, this isn't pentane, it's a branched alkane. So we have butane, so 4 carbons, and there's the 5th one to match pentane. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So this is 2-methylbutane, but it has the same molecular formula as pentane, but it has a different arrangement of atoms. So their structural formula is different. Their properties are going to be different as well. And that's what a structural isomer is. So cyclic hydrocarbons are when carbon chains form rings to make cycloalkanes or alkenes. We can use geometric shapes for this, with each angle representing each carbon. So the first one, if we drew a triangle, that would be cyclopropane. A square would be cyclobutane. A pentagon would be cyclopentane. And then a hexagon would be cyclohexane, and so on. You could draw the carbons out like so. I'll do the first one for this one. So this would be H2C, a line, CH2, another line over here, H2C, and so on. So you might wonder why sometimes we draw the methyl group backwards. We want to make sure that the carbon is the thing that's involved in the triangle or whatever geometric shape. So we might need to write the atoms in backwards order, so to speak. So when we draw structural formulas, we draw the bond angles at 90 degrees and 180 degrees, but this isn't reality. Single bonded carbons have bond angles of 109.5 degrees and take a tetrahedral shape, and double bonded carbons take a trigonal planar shape, and the bond angles are 120 degrees. So we use stereochemical formulas to represent the 3D structure of organic molecules. So how to draw a stereochemical formula? A bond sticking out from the plane is shown as a solid wedge, and a bond sticking into the plane is shown as a dashed wedge. So if we were to draw methane, for instance, we would put our central carbon, one sticking straight up, one going off here. Then we would draw a solid wedge to show that it's coming out of the plane, and then a dashed wedge showing that it's going into the plane to represent that tetrahedral shape. Now, if we were to draw ethene, it would look like this because it's taken the trigonal planar shape. So instead of drawing the hydrogens at right angles, we draw them this way to show the 120 degree angle.